Discrete random variables. Another wonderful resource from Dr. Frost. I have adapted it though to suit our chapter, okay? So, what we're going to be looking at discrete random variables is the difference between this and GCSE is mainly the notation, and the notation is how we write something and why. And we're also going to be looking at different ways of looking at the expected, okay, and the variance. Okay, so we are going to extend our knowledge a bit. So, a random variable x represents a single experiment or trial, and this is a capital X, okay? So, and then the little x is the particular outcome. So this is the probability of this trial being a 1, for example, okay? Now, the probability of x equaling x is the probability of x, okay? And we have the lowercase p, because this is saying the probability that the outcomes of my coin thrown was heads is the probability with a capital P of x. And this is the probability of heads, okay? The more we get to use this notation, the better we will feel. So, discrete random variable. What are they? So, the height of a person is not discrete, and that is because it is continuous. The number of cars that pass in the next hour. Is this a discrete random variable? Yes, because this is based on trial and an experiment. And the number of countries in the world. This is not a discrete random variable because there are a set amount of countries in the world. They may change from time to time. When we lose a country, we gain a country. But essentially, this is roughly the same, okay? It doesn't vary. So what we're going to have is we're going to look at the difference between a probability distribution and probability functions. So probability functions are when we write the probability of x is 0.1x when x is 1, 2, 3, or 4, or 0, and that's otherwise, okay? What this means is, and I'm going to show you what this means in terms of a distribution because we will understand the distribution. When x equals 1, the probability of x, and here we have 1, 2, 3, 4, is 0.1 times x, which is 0.1 times 1, which is 0.1. The probability when x equals 2 is 0.1 times 2, which is 0.2. The probability when x equals 3, 3 times 0.1, which is 0.3. And then the probability when x equals 4 is 4 times 0.1, which is 0.4. Now, as we know as well, probabilities should add up to 1, okay, especially when we're looking at the trials. Now, the advantages of the probability function is the fact that we have a rule. Okay, we've got a rule going on, 0.1x. We've got an expression based on the outcomes. And this is going to be really useful in statistics too when you look at continuous random variables, because it would be impossible to list all of the variables. Here, we can say, x could belong to a certain amount of numbers, and here we could say that. Whereas the advantages of this distribution, is that we can see every single outcome. The probability of every outcome is there, okay? So, the probability of every outcome is shown. Okay, so we're going to do an example. The random variable x represents the number of heads when 3 coins are tossed. So when we did GCSE, we would be looking at a sample space diagram. Now, a sample space diagram of the 3 coins that are tossed is all the possible values. If you think about this, we could have 3 coins, we know. We could have heads, heads, heads. Okay? We could have heads, heads, tail. We could have heads, tail, heads, tail, heads, 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 tail, 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 heads, tail, 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 heads, tail. 1, 2, 3, 4, 5, 6, 7, 8. Okay, that is all the possible combinations. I'm going to come to how I know this is all the possible combinations, okay? Right, now the probability distribution. This is very simple, isn't it? Okay, it's the number of heads when 3 coins are tossed. So if we think about it, number of heads is what our x is going to equal. When 3 coins are tossed, what are the possible number of heads? We could have 0 heads shown. We could have 1 head shown. We could have 2 heads shown, or we could have 3 heads shown. Okay? So the probability of within our experiment being a certain amount, okay, is, what is the probability of 0 heads being shown? 1 out of a possible 8. What is the probability of 1 head being shown? And it's 3 out of possible 8, because there's only 3 in here which have 1 head. Probability of 2 heads being shown? 3 out of possible 8. And what's the probability of 3 heads being shown? 1 out of 8. Okay, so from the question, what we've done is we have represented this as probability distribution. Now as a function, okay? Now this one will take some practice, but it is really simple, okay? And what we call this is a piecewise function, because we're saying in this function there's 2 rules. Now what I notice is that it's 3 over 8 when x is 1 and 2, or it's 1 over 8. So I can write this as a function. Probability of the outcomes equaling x is going to equal. Now, it's going to equal 1 over 8 when x equals 0 or 3. It's going to equal 3 over 8 when x equals 1 or 2. Or we're going to put 0 and then we're going to write otherwise. Now, in our case, there is no otherwise. Okay? Because these are the only possible, but we still have to write otherwise in the formula, because the formula doesn't, the probability function, when you're given that, you can't see your sample space diagram. You may not know the context, you may just be given the function. So this is why it has to, every single possibility. If it's 0 and 3, you get 1 over 8. If it's 1 and 2, you get 3 over 8. If it's anything else, it's 0. So, sometimes it asks you for a probability in a range of values. So this is figuring out what this means. This is really simple. This one's the probability of our outcomes to be in between 1 and 5. What numbers are in between 1 and 5? 2, 3, and 4. So that means this essentially wants the probability of 2 or 3 or 4. So we add them all up, and we're going to get 0.75. Okay, the next one, what's the probability of including 2 and 4? So this is the same again. This is the same as 2, 3, 4. which we know is 0.75. The next one wants the probability between 3 but including 6. Okay, so this is just 4, 5, 6, which is 0.4. And then the next notation wants the probability of any outcomes where x is less than or equal to 3. So 1, 2, 3 is what we want, which is 0.6. Okay? So now we should have a bit more understanding that this is looking at the probabilities of x's outcome being between 1 and 5. So, a typical exam question. A discrete random variable x has this probability function. And it's basically saying that x equals -1, 0, 1 and 2 and 0 if otherwise. So if you were to write this as a probability distribution in a table, okay, now you don't have to use a table. So we're going to have x is -1, 0, 1, 2, then our probability of x equaling x. If I substitute in -1 into here, I'm going to have 1 minus -1, which is 2, squared, which is 4, multiplied by k. This is 4k. Is that like HD? 4k. Yeah, it is. Okay. Then, we're going to substitute in 0. 1 minus 0 is 1. 1 squared is 1, multiplied by k, it is k. Then we're going to substitute in 1. 1 minus 1 is 0. 0 times k, 0. Then we're going to substitute in 2. 1 minus 2 is -1. -1 squared is 1, multiplied by k is k. So here we have our probability distribution. Now this is back to GCSE. We have a distribution. And what do we know? It then says the probability is 0 otherwise. That means the probability is 0 if x does not equal one of these outcomes. So this must mean this is the total possible probabilities. And we know that all this probability should add up to 1. So essentially we now have to make an equation. 4k plus k plus 0 plus k equals 1. 6k equals 1. Therefore, k equals 1 over 6. Therefore, proved. Okay, question 6a, nice and easy. I would always recommend drawing a probability distribution table if you're not sure. In here, you can see our x values are 1, 2, 3 or 4, because it's told us that. And then it's told us to find the probability of each individual value. Our formula is k multiplied by x. So the probability of x equaling x is k multiplied by x. 1 times x, 1 times k, k. 2 times k, 2k. 3 times k, 3k. 4 times k, 4k. And then we know, because these are the only outcomes available for this specific probability, that k plus 2k plus 3k plus 4k should add up to 1. I now have 10k. Well, I wish I had 10k. That adds up to 1. So k is in fact 1 over 10. Nice and simple. Question 6. Now for this one again, it says find the value of k, but personally I would always construct a table. Write down what's inside and then find the values of k. So if I was to construct a table, we have our values of x. Now if I have a look at what my values of x are, here they are. Here are my values of x. So my x is 1, 2, 3 or 4. 1, 2, 3, 4. Okay? Then, to find out the probability of the outcome equaling our specific value of x. If I want to know what the probability is when x equals 1, my 1 is here, so I have to use this formula. This is k times 1, which is k. The probability when x equals 2 is here, so I have to use this formula. 2 minus 1, 1 multiplied by k, k. 3, use this formula, 3k. 4, use this formula, also 3k. So I know, because really it should say 0 and it should say otherwise, okay? But it doesn't. That's all right. But if it's not listed, that's what it means. And if it says 0 otherwise, it means there's no anything else. You know, if x is otherwise not this, the probability is 0, okay? So I know that k plus 3k plus 3k equals 1. 8k equals 1, k equals 1 over 8. Then, part B says to construct the table given the probability. So you will have to draw the table out again, but I just think it's good practice. 1, 2, 3, 4. So we know the probability of getting 1 is 1 over 8. Probability of 2, 1 over 8. Probability of 3 is 3k, 3 over 8. Probability of 4 is 3k, 3 over 8. Now I can double check I'm right, because all these probabilities should add up to 1. 1 over 8 plus 1 over 8 plus 3 over 8 plus 3 over 8 equals 1. I know I'm wrong. The cumulative distribution function. Okay, this is basically cumulative frequency. So if we were to express the probability that the age of someone is at most 40, okay, we're pretty much saying we don't want anyone to be if they're at most 40, anyone older than 40, we don't want to know. We could write that as the probability of the age being less than or equal to 40, because this means the probability is at most 40, okay? This, using our cumulative distribution function, would mean that we want f of 40. So, the rule is, if we have the probability of a number of the outcomes that we want being less than or equal to our value of x, we write fx, okay? This is what we write. This is a rule. For example, if x is the number of heads thrown in 2 throws, what is the probability that there are 0 heads thrown? So it's 2 throws. So again, we're going to have heads, 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 tail, tail, heads, tail, tail. What is the probability that 0 heads are thrown? 0.25. What's the probability that 1 head is thrown? It's 2 out of 4, which is a half, isn't it? 0.5. And what is the probability that 2 heads are thrown? 1 out of 4, 0.25. How do we know we're correct? Because all of these add up to 1. Perfect. Okay, now, our f of x is practically our cumulative frequency. Okay? So, the probability of f of what? Of 0 is 0.25. Okay? And remember, f of 0 means the probability of our x, okay, being less than or equal to 0. So what's the probability that we have no heads? Our f of 1 is cumulative frequency, so 0.25 plus 0.5, 0.75. So we're saying, so our f of 1, that second one we worked out, is saying what is the probability of our outcomes being less than or equal to 1? So what's the probability of getting 1 head or less? Okay? And this is why this is why we write it in this R notation, because we want the probability of our outcomes being something. Okay? And then the last one is what f of 2, which is what is the probability of our outcomes being less than or equal to 2? Well, that's 1, isn't it? Because if we were cumulative frequency, everyone's happy with cumulative frequency. 0.25 plus 0.5 is our next one. And then this plus 0.25 is the next one. Yeah? Okay? But of course, having the outcomes being 2 heads or less is going to be 1. It's certain. Remember, because in probability, 1 is certainty. Okay. So, this is a typical type of question. And it says, the discrete random variable x has a cumulative distribution function. So this time, when they say they're giving you a function, they're saying this is the formula. Okay? This is the formula. It says find the value of k. Now, when we just looked at our previous example, we know that if we have x here, and we have f of x, our x is 1, 2, and 3. 1, 2, and 3. Now, we know the last value of x is going to be a whole 1. Why? Because it's certain, because it's cumulative frequency. Remember back in GCSE where we'd say, you know, we took the weight of 100 people, and they put it in the brackets, don't they? And when you did your cumulative frequency, what should they all add up to? 100. Okay? So, knowing this fact, you then know that f of 3 equals 1. Okay? And in this case, your x is 3, isn't it? So we could use that into our formula. That means 1 equals x plus k over 8. But we know that when f of 3 equals 1, that our x is 3, isn't it? So 1 equals 3 plus k over 8. So 8 equals 3 plus k. So therefore, k equals 5. So k equals 5. Nice and simple. Knowing the facts, remember, one of the facts are, whatever our last value of x is, that f of x will always be 1. Next it says, draw the distribution table for the cumulative frequency distribution. Now we already know that k equals 5. So our formula is f of x equals x plus 5 divided by 8. So in this case, we're going to have 1 plus 5 is 6 divided by 8. What is 6 divided by 8? 3/4 actually, isn't it? 0.75. Now our f of 2 is 2 plus 5 divided by 8. 7 over 8. What is that? 0.875, is it? Yeah? 0.875. And then we know f of 3 equals 1, because remember, it's cumulative distribution function. Now it says, write down f of 2.6. Okay. So, this is where, if we're to write down f of 2.6, f of 2.6 can be found in here somewhere. Okay? Now we know f of 2.6 we don't have. So we need to round down. So this is saying we want f of 2. Now f of 2 is easy. It is 0.875. It then wants you to find the probability distribution of x. So this time we're working backwards. Okay? So, we know the probability distribution of 1 is 0.75. I haven't added anything to that. 0.75 plus what gives me 0.875? And it's 0.125. And then from 0.875 to 1, what did I add on? 0.125. So I've worked backwards to find my actual frequencies, which in this case is my actual probabilities. And again, what should they all add up to? 1. So the discrete random variable x takes the values 1, 2 and 3 and has a cumulative distribution function given. Find the probability distribution of x. So we need to draw the table of x and of p of x equals x, and we know we have 1, 2, 3. Now we know the outcome of the probability of a 1 is 0.4 because it's the same as on the cumulative frequency. Then I look at the difference between 0.4 and 0.65, 0.25, and then the difference between 0.65 and 1, 0.35. Okay, so that's a nice and easy 3 marks. Part B says find the value of f of 1.8. Now we don't have 1.8, so we round down. This is going to have to be f of 1, which is 0.4. Okay? The discrete random variable x can take only the values 1, 2 and 3. For these values, the cumulative distribution function is defined. Now, if it can only take these values, that means the last value of x, our cumulative distribution will equal 1. So this means f of 3 equals 1. So I can now use this. 3 cubed plus k over 40 equals 1. That then means 27 plus k equals 40, k equals 13, therefore proved. Nice and simple. It now says find the probability distribution of x. Okay, it's really important that you know it says here probability distribution of x. If you want to start with the frequency, the cumulative frequency distribution, you can do that and then work your way backwards. So we have f of x, and we know the only values are 1, 2 and 3. So we know if k is 13, we know for 3 this is 1. If we substitute in our value of 1 in here, we're going to get 1 plus 13 is 14 over 40. 14 over 40 is a decimal 0.35. Then when we substitute x equals 2, we're going to get 8 plus 13 is 21 over 40. 0.525. This is our cumulative distribution here. What we want is it clearly states the probability distribution. So we're going to have x, and we're going to have p of x equals x. Again, our only outcomes are 1, 2 and 3. We know the first one's 0.35. 0.525 minus 0.35 is 0.175. And then 1 minus 0.525 is 0.475. And that is how we get the 4 marks. So what we're now going to look at is expected value. And the notation for this is capital E and capital X. Okay. Suppose we throw a single fair die 60 times. And what we expect is this. And we were speaking about this earlier. We'd expect we know the probability of the outcome of X is how many chances are there of getting a 1? 1 out of 6. How many chances are there of getting 2? 1 out of 6, okay? This is the kind of probability distribution here. But when we started throwing it, okay, what happened? We got 9 1s, 11 2s, 10 3s, 8 4s, 12 5s, and 10 6s. So the mean outcome based on our sample. So we have to work out the mean of this. Now we all know how to work out the mean. How would we do that? 1 times 9. Okay. Yep. So what are we going to have? Remember, there's a frequency table here. So 1 times 9. How could you do this quicker? Yeah, put it into your calculator. 3 times 10. 4 times 8. 5 times 12. 6 times 10. And I'm going to divide it by 60. So the mean outcome based on our sample is perfect. And this is going to equal 3.55. Okay? But using the actual probabilities of each outcome, okay, the 1 over 6, because these are the actual probabilities. If we did 1 times 1 over 6 plus 2 times 1 over 6 plus 3 times 1 over 6 plus 4 times 1 over 6, okay, what would the expected average be? Okay, it would be 3.5. Okay, now how do we get this? It's the sum of our x multiplied by our probability of x. Okay, so for our third dice, we've just worked it out anyway, and it's 1 times 1.6 plus 2 times 1 over 6, not 1.6, sorry, plus 3 times 1 over 6 plus 4 times 1 over 6 plus 5 times 1 over 6 plus 6 times 1 over 6 divided by the total of probability, which is 1. So we don't need to divide it by 1, okay? But that's how we would normally work out the mean. So the formula is the sum of our x multiplied by the probability of x is what our expected value is equal to. Okay, just to clarify, we would expect it to be about 3.5 because it's in the middle of 1 and 6. Okay? But we have an actual formula to use. Okay, really quickly, can you find the expected values of each of these probability distributions? And you should be able to do this in your head. Okay, so the first one, we know expected value is the sum of x multiplied by the probability of x. So 1 times 0.1, 0.1. 2 times 0.6, 1.2. And 3 times 0.3, 0.9. Add them all up, 2.2. Okay, I've written these down, but we should be able to do these in our head. For the next one, 4 times a half, 2. 6 times 0.25, 1.5.
I found this on the web.
Oh. 8 times 0.25, 2. Add them all together. 2 plus 2 plus 1.5. 5.5. For the next one, now, as you can see, this one is symmetrical, isn't it? It goes a quarter, a half, a quarter, okay? It's symmetrical about this one. Fun fact, the expected value will then be 20, but we can double check that. 10 times a quarter, 2.5, a quarter times 30, 12.5, and half of 20, 10. No, 7.5, 2.5 and 10, which is 20, okay? Okay, 10 times a quarter, 2.5, 30 times a quarter, 7.5, 20 times a half, 10. We add them all up, we should get 20. Okay, here we have a bit of a harder example, okay? So, this one, we're going to use our favourite thing ever. Simultaneous equations. Right, what facts do we know? First of all, the facts we know is that our expected value is x. How do we find our expected value? By doing the sum. 1 times 0.1, 0.1. 2 times p, 2p. 3 times 0.3, 0.9. 4 times q, 4q. 5 times 0.2. And we all know that 5 times 0.2 is 1. Okay. Now our expected is 3, which equals 2 plus 2p plus 4q. So that means 1 equals 2p plus 4q. So we've got two unknowns. We need a simultaneous equation. What else do we know? We know that all of these probabilities should add up to 1. So I'm going to do this really quickly. And we should have 1 equals 0.6 plus p plus q. So I'm going to rearrange this to get p equals 0.4 minus q. I'm going to substitute that in, and we should all be happy with simultaneous equations now. So we're going to get 1 equals 0.8 minus 2q plus 4q. 0.1 equals q is what I got. Please somebody check that. If 0.1 equals q, that means p equals 0.3. Okay, let's just double check we're right. 1, 2, 6. Yep, okay, perfect. So we're just going to have a look at something a bit different. So remember when we did the mean of the squares? Yeah? So when we find variance, we know we have to do the sum of fx squared divided by the sum of the frequency, okay? What we're going to do here is pretty much the same. What we are going to do, though, is we are going to look at the sum of x squared and the expected of x squared. So expected of x squared is really simple. We're going to square x and then multiply it by the probability. So we're going to have 1 squared multiplied by the probability plus 2 squared, which is our x, multiplied by the probability, plus 3 squared multiplied by the probability. Once we do all that, then you get 5.7. Okay, for e of 2x, what are we going to do here? Two times yes, 2 times 1 times 0.1 plus 2 times 2 times 0.5 plus 2 times 3 times 0.4. 4.6. So to find the variance, we know, yeah? Mean of the squares, which is going to be this, minus the square of the mean. Okay? So it's still the same formula, except for this time our square of the mean, our means are expected outcome. Okay? So, to work out the variance, now lucky for us, we've already done this on the previous page, okay? We just did this. But I am going to do it again just to make sure we're happy. So, our EA, our expected of our x squared is going to be 1 squared times 0.1 plus 2 squared times 0.5 plus 3 squared times 0.4. And this is going to give us 5.7. So 5.7 minus, and then our mean is going to equal 1 times 0.1 plus 2 times 0.5 plus 3 times 0.4, okay, which is 2.3. And we know we need to square 2.3 when we take it away. So that means our variance is 0.41. So the discrete random variable x has probability distribution given by, and it says where a is a constant. Now here, clearly you can see we have two a's, okay? Now, if it says a and a, they obviously represent the same number, okay? So we add them all up, I can see I've got 2 over 10, 2 over 10 is 4 over 10, 5 over 10. So this is going to be a half divided by 2, which is a quarter. It then says write down E of x, the expected. Now, we just saw in a previous one, if we have a symmetrical distribution. Now, here we do have a symmetrical distribution because on either side of the probability of the middle number is 1 over 4 and a fifth, and here we have 1 over 4 and a fifth. So straight away, I know the answer is 1 because this is a symmetrical distribution. And you can see it's given by 1 mark. Alternatively, you could have just put it into your calculator and you could have just done minus 1 multiplied by a fifth plus 0 multiplied by a quarter plus 1 multiplied by 1 over 10 plus 2 multiplied by a quarter plus 3 multiplied by a fifth. And when you worked all this out, you would have got the value of 1. Okay, and then it says find the variance. Okay, mean of the squares minus the square of the means. Okay, now for the second one, again, we're going to have minus 1 squared multiplied by 1 over 5 plus 0 squared multiplied by a quarter plus 1 squared. And once you put this into your calculator, you're going to get 3.1, and then we're going to minus our expected value, which is 1 squared. So the final answer is 2.1. Right. When Rohit plays a game, the number of points he receives... Sorry, everyone, I don't know what this is given by the discrete random variable x with the following probability distribution. It says find E of x, okay? 0 times 0.4 plus 1 times 0.3 plus 2 times 0.2 plus 3 times 0.1, 1. Find f of 1.5. Remember, this is the probability of x being less than or equal to 1.5. Now, we then round down. So this is the same as the probability of our distribution being less than or equal to 1, which is the commutative frequency. Now, if I was to just draw this commutative frequency here, our f of x, I'm going to have 0.4, 0.7, 0.9, and 1. Okay, so that's going to be 0.7. Then it says, show that the variance equals 1. We've got E of x, we need E of x squared minus E of x all squared. We need to show that equals 1. Well, E of x all squared, now when it says show that, you've actually got to show all your work in. 0 squared times 0.4 plus 1 squared times 0.3 plus 2 squared times 0.2 plus 3 squared times 0.1, all in a bracket. We're going to minus 1 squared. This is going to give me 2 minus 1, which equals 1. Therefore, proved. Coding, one of our favourite topics. So remember when we coded here, okay? So we have a list of people's heights. The mean of their heights is 1.5 and the variance is 0.2, okay? So the variance is 0.2. Now remember in coding, when we're doing the mean, what do? We do everything it says. So when we're coding with the mean, we just substitute our mean value into here and do exactly as it says, okay? So if we want to find the mean of y using the coded data, we're going to do 3 lots of the mean of x minus 10, which is 3 lots of 1.5 minus 10, which is 4.5 minus 5.5. And And as we know, the variance is the standard deviation squared. So when we're looking at how it affects it, normally when we were doing standard deviation, we would just multiply it by, in this case, 3. But because the variance is the standard deviation squared, to find the variance squared, we would have to square all of this. So this is actually going to become 3 squared lots of, I don't know, sorry why I've put x, lots of our variance, which is going to give us 9 times 0.2, which is 1.8. Okay, so the same below with our expected value here. E of x plus 10 is just the same as finding e of x and then adding 10. E of 3x is the same as 3 lots of e of x. Our variance, now remember it's the standard deviation squared, so this is the same as 3 squared lots of our variance of x. Okay, so very quickly, with the rules of coding, okay, if we have e lots of ax plus b, where a and b are constants to be found, what do? This is the same as doing a lots of our expected value and then adding b, okay? For variance, if we have variance of ax plus b, then our answer is going to be a squared variance of x, okay? These are the 2 rules. So, very quickly. So, instead of multiplying all of our expected outcomes by 4 and adding 1 to them and then multiplying it by our probability, we don't need to do that. What we can do is by using this coded data, we know this is the same as finding our normal expected value, but doing 4 lots of our expected value and then adding 1 to it. For the second one, this is the same as doing minus our expected value plus 1, because you have to figure out your a is your coefficient of our capital X and your b is your constant. The variance of 4x, that's the same as putting your a is 4, so this is 4 squared, which is 16 lots of the variance of x. For the second one, we have the variance of x plus 1. Have I multiplied x by anything? No, so this is just the same as the variance of x. For the next one, all I've done is 3x plus 2. Again, our a is 3, it doesn't matter what our b is, okay, using the rule. So 3 squared is 9 lots of the variance of x. E lots of x minus 1 over 2. So this is going to be e of x, take away 1, and then I'm going to divide all of it by 2. Then for the last one, I've got the variance of x minus 1 over 2. So what have I done to x? I've divided it by 2, so I need to, well, multiply it by a half, shall we say. So I'm going to bring that outside, a half squared, which is a quarter lots of the variance of x. So, if e of x is 2 and the variance of x is 6, find e of 3x. We know this is the same as 3 lots of e of x, which is 3 lots of 2, which we know is 6. For the second one, d, we know, e of 4 minus 2x is exactly the same of 4 minus 2 lots of e of x. So 4 minus 2 lots of 2 is 0. And then for the last one, we've got the variance of 3x plus 1. We know this is exactly the same as 3 squared lots of the variance of x, which is 9 times 6, which is 54. And then for the second one again, I'm going to do the exact same, and we should get 7, 81. So with the third one down, e of y squared. Now, we know this is the same as the expected of y all squared plus the variance of y, okay? And this comes from where we know that the variance of y equals the square of the means. Oh, sorry, that's supposed to say an e. The mean of the squares minus the square of the mean, okay? And this is how we've got that. Again, you know all the skills. So when we do, we're going to have 2 squared plus 9, 13. And then for the second one, we should be able to spot that this is the difference of 2 squares. So this is the expected value of y squared minus 1, okay, which we know is the expected value of y squared minus 1. We've just worked that out, so 13 minus 1 is 12. So, problem solving. So, provided that a coding y equals f of x is a one-to-one function, we can determine the original expected value and variance given the expected value and variance, okay? So, we know that x is a discrete random variable. The discrete random variable y is defined as follows. Y equals x minus 150 divided by 50. It's given that the expected value of y is 5.1 and the variance of y is 2.5. We need to find the expected value of x. Well, this is really simple because we know to find the expected value of x, we're going to have e of x minus 150 over 50. E of y is going to equal e of x minus 150 over 50. So we know what e of y is. We know it's 5.1. So we're going to have 5.1 equals e of x minus 150 over 50. So we're going to do 5.1 times 50 plus 150 is going to give me e of x, which is 405. And then part B, we know with the variance of y is going to equal the variance of x divided by 50 squared. Now, remember, we don't care about the add or minus with variance, and if you remember from earlier chapters, why. So this is going to be 2.5 as our variance of y equals the variance of x over 50 squared. 2.5 times 50 squared is going to equal 6,250. So that is the variance of x. Okay, another question. So the discrete random variable x has a probability distribution given by the discrete random variable y is defined as y equals 3x minus 1. Given that the expected value of y is minus 2.5 and the variance of y is 13.95, find the expected value of x and the expected value of x squared. So first of all, the expected value of y equals 3 lots of the expected value of x minus 1. We're going to get minus 2.5 equals 3 lots of ex minus 1. So I'm going to add 1 to both sides and then divide by 3. So therefore, my expected value of x is minus 0.5. Now, how do I find my expected value of x squared? Now, we already know so we know the variance of x equals our expected value of x squared minus our expected value of x all squared. So what I need to do is find the variance here, and because it's told us the variance of y, then rearrange and find the answer. So I know my variance of y. So this is going to equal 3 squared lots of our variance of x. So I'm going to have 13.95 divided by 9, which is going to give me 1.55. So that's my variance of x. So now I know that to find the expected of x squared, I'm going to have the variance of x plus my expected value squared, which is going to be 1.55 plus minus 0.5 all squared, which is going to give me 1.8. So that's part A done. Nice and simple. It now says part B, the values of A, B and C. Well, first of all, we know a few things. Number one, we know that probabilities add up to 1. So 0.3 plus A plus 0.25 plus B plus C equals 1. Okay, what else do we know? We know our expected value equals minus 0.5. And how do we work that out? By multiplying together. So minus 2 times 0.3 is minus 0.6. Minus 1 times A is minus A. 0 times 0.25 is 0. 1 times B is B. 2 times C is 2C. We know this equals our expected value, which we worked out in A, is 0.5. Minus 0.5, sorry. Then, what else do we know? We also know how to work out our expected values of x squared, and we worked that out. That was 1.8. And how do we do that? We do it by doing minus 2, squaring it, and then multiplying it by 0.3. So 4 times 0.3 is 1.2. 1 times A is A. 0 squared times 0.25, 0. 1 squared times B is B. 2 squared times C is 4C. And this is going to equal 1.8. You're going to have 3 simultaneous equations now, and the reason why we had to have 3 equations is because we've got 3 unknowns. Rearrange, substitute, work it out to find the values of A, B and C. So once you do all of that, you should find that A equals 0.2, B equals 0.2, and C equals 0.05. And then part C says, find the probability where our outcomes of X are greater than our outcomes of Y. So this is a probability when our outcomes of X is greater than our outcomes of Y. Now we already know what Y is defined by, and this is defined by 3x minus 1. So I'm going to rewrite this as the probability of when our outcomes of X is greater than our 3 lots of our outcomes minus 1. Rearrange this. If I take away 3x from both sides, and I'm going to divide everything by negative 2, I'm going to end up with the probability that x is less than positive a half, okay? So, where are my outcomes less than a half? And it's these 3 here. 0 is less than a half. Minus 1 is less than a half, and minus 2 is less than a half. So I'm going to add 0.25 plus my A, which we know is 0.2, plus my C, which is 0.3, which gives me 0.75. Okay, so the last thing this chapter is looking at discrete uniform distribution. And the best example of this is a dice, because the probability of each outcome is the same. There's 1 in 6 chances for 1, 2, 3, 4, 5, and 6. So the probability of x is known as a probability mass function, because the probability of each outcome represents an actual amount, as in there are 1 in 6 chances, like 6 faces. And for this, we have 2 rules. Our expected value is n plus 1 over 2, where n represents our possible outcomes, and our variance is n plus 1 multiplied by n minus 1 over 12. So, give this a go first, but digits are selected at random from a table of random numbers. Find the mean and standard deviation of a single digit. Well, first of all, if digits are selected at random and we have single digits, what are the single digits available? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have a possibility of 10 digits, okay? So the outcomes is 10. 1, 2, 3, 4, 5, 6, 7, 8, Okay, just double check. Right then, so then our expected value is going to be 10 n plus 1 over 2, which is 11 over 2, which is 5.5. And then our variance is going to be n plus 1 multiplied by n minus 1 over 12. So we're going to get 11 times 9, which is 99, divided by 12, which is 8.25. So it wants the mean. So our mean is, okay, so our standard deviation is the square root of our variance, which is the square root of 8.25, which is 2.87. And then part B says, using the value of theta, find the probability that a particular digit lies within one standard deviation of the mean. Okay, so we want to know if picking a digit, x, lies in one standard deviation of the mean. So we're going to have, for example, 5.5 plus 2.87, because this is one standard deviation. 5.5 minus 2.87. Oh, and I've just realised I've gone wrong in part A. Okay. In part A, I've gone slightly wrong, because actually my expected value should be the middle of these. But this is assuming that we started at 1. And we didn't, we started at 0. So if I was to actually work out the median, essentially, you're going to see, what a silly error to make, but at least we made it. You're going to see that the middle is actually between 4 and 4.5. So double check for that. This formula only works if you're starting from 1. Okay, so this is 4.5. We would have to take away 1 from this. So on the second part of the example, question, you can have 4.5 and 4.5. Sorry for the mistake, everyone. But if anyone did spot it, well done. Which is then going to give me, so we want the probability of this, which is the probability of 4.5 minus 2.78. 1.63 is less than x, 7.37. Okay, so we want x to be in between these values. Now, as we know, so if we look at this in terms of whole numbers, the probability is going to be, it's not going to be quite including 1, because it will include 2. And also it's going to be less than 8, but it will include 7. So when we're looking for our probability, what values are between 1 and 8? 2, 3, 4, 5, 6, 7. So that's a total of 6 out of 10 possible values, which is 3 out of 5.